Okay, so here is the suggested solution to the, I still didn't have time to think about the tangent space. This is about the other one, y perp is equal to y. So the question here is the following. So let me recall the question. X, so G is a diagonalizable group. X is the character group of G. So Y, so this is a finitely generated abelian group with no p torsion. Subgroup such that x mod x by y, x mod y has no p torsion. Then show. So this is the exercise. Right, and what is y perp? So y perp is all those elements, is a subgroup of G. Right, it's all those G in G such that chi of G equals 1 for all. Right, this is a closed subgroup of G. Why? Because this condition, it's saying chi is a continuous function, is the inverse image of 1 under chi. That's a closed set, and then you are intersecting over all G in G, overall chi in Y. Right, so that's a closed. So this y perp is a closed subgroup of G, and then y perp is by definition all chi in X such that chi restricted to y perp is identically 1. Right, and what is obvious, one of these containments is obvious. Right, this is obvious because what does this mean? So surely chi, if chi belongs to y, then chi restricted to y perp is identically 1. Okay, so here is the suggested solution. Look at x going to x by y. Right, this is the natural map of abelian groups. Right, so not k, what is that now? If you have a map of groups, then there is a natural map of group rings. Right, this kx is, I didn't write bracket, but so that's our notation for a group ring. Right, so what is kx? Kx is kg, right? G is a diagonalizable group, right? That's what is this? Well, claim is this is equal to, so this is equal to this is an onto map, this is an onto map. So proof is that, observe so what is the kernel here of this? So the kernel at this level is y, right? Of the abelian group morphism. This is the kernel. So I can write this. That's an exact sequence. So here the claim is the kernel of this. Well, actually I don't need it. All I need to say is the following. See, the point of the observation is the main idea is, what does this mean? This means that this is reduced. Okay, so if you have so it must be the group the ring of functions on y bar, y perp. Why? Because what have you gone modulo? See, if you think through this, you've gone modulo chi minus 1 chi in. So if I claim the kernel of this map is chi minus 1 chi in I, chi in y, the ideal generated by that. Surely that is in the, okay, so what you need is that surely that is in the ideal that is in that, all that goes to 0. Every element of, if chi is in y, when I map it here, it becomes equal to 1. So that's surely in the kernel, right? Now it's a reduced ring, and so if I have some bunch of elements whose 0 set is, okay, so I want to okay, how do, so I want to, what situation are we in? I'm given an ideal, I'm given a subvariety. The subvariety here is y perp, and the ideal I am given is this, or rather the kernel of this map, whatever that is. Okay, I want to show that that ideal is the ideal of that subvariety. This is what I want to show. Okay, the ideal is the ideal of that subvariety. What all do I need to check? If I check that all the elements in the ideal vanish on that subvariety. Okay, first, suppose I do that and show that that ideal is reduced. Maybe I need more. Okay, sorry, I'm saying this wrongly. That the variety is defined by the elements of the ideal, and the ideal is reduced. These are two things enough, right? So I claim, so look at the kernel here. So let's call the kernel k, right? So let's call the kernel let's call this map pi. Let k be equal to kernel of pi, right? Claim variety of k is equal to y perp. Okay, this is one claim. Let me not try to prove that. I mean that I claim that's easy to see. Okay. Then furthermore, that this is reduced, right? So claim 1, claim 2. That claim 2 follows from the fact that x mod y has no torsion. Now we are all right. Right? Because now I take an element here, if I have a character here, which is, now I want to show something y per perp means what? It should become 1. It should, so if an element of x goes to 0, yeah, suppose some element belongs to y per perp, that means it is 0, that it goes to 1 under this map, right? Which means that it must be the kernel, I mean it must belong to y, because as a character it becomes 0, right? But as a character it cannot become 0 unless it is in y. Right? I mean, is that okay? Because if I take something not in y, that's a non-zero character here. I mean, non-trivial character here, not non-trivial character here, and therefore it cannot be identically 1 on y perp. Because it's the ring of functions on y perp.
So you have to prove that K of x mod y is the ring of functions.
So that follows from these two claims.
You have that y perpendicular is V of y perpendicular whole perpendicular minus 1. That is I am given.
You are given that?
I can show that y perpendicular is equal to V of y perpendicular whole perpendicular minus 1. It's the elements.
Okay.
So if I have to show that V of k is equal to y perpendicular, so essentially I will be showing that means k is actually y, right?
K is y minus 1.
Yeah. K is equal to y minus 1.
Yes.
So y minus 1 is contained in y perpendicular whole perpendicular minus 1.
No, V of k is equal to y perpendicular. What does that mean? That is just exactly this statement.
Yeah, so how do you prove the V of k equal to y perpendicular?
That is, I claim this is that statement. This is V of k.
What is the V of that is y perpendicular. That is V of that is V of k.
This is V of k.
Yeah. So I of V of k will be radical of.
We are not saying I of V. We are not talking about I of V of k. We are only saying V of k is equal to y perp.
Okay, V of k is y perpendicular.
Okay, if you believe that for the moment, V of k is y perp, and the thing is k is reduced. I mean modulo k is radical. The point is k is radical. The new thing that the new thing here is that this is a reduced thing. That's what you have to use. I mean, I see what you're saying. I also try to write it by element wise, and it looks, you have nowhere to go. Sort of, I couldn't. see where to go. The point here is that this ring is reduced. You have to use that. That's a new.
Can you just last if I take these two claims?
Yeah.
So now what is the conclusion? I mean, what is the last thing that is what is the conclusion?
Yeah, the conclusion is, so from, it's okay, claim 1, okay, so I'm not giving you the proof, so to speak. I'm reducing the proof to 2 claims, okay, which if you convince yourself, okay. If there are problems with these 2 claims, do come back and we'll. So this claim 1 and claim 2, as Gautam says, we grant that, and then how does it follow is the question, okay. So so from these 2 claims, what follows is that V of I of y perp is equal to k. So this for okay. Now, if suppose this containment were strict, there was an element of y per perp which was not in y. Okay, what would happen? Take that. So let's call that chi. Chi minus 1 would, so take chi in x, right? So chi minus 1 would be 0 here. That's what it means to say I of y perp. It's a chi minus 1 belongs to y per perp chi belongs to y per perp means chi minus 1 belongs to I of y perp, right? But such a thing is not possible because an element of x cannot be 1 unless it belongs to y. So chi minus 1 cannot be 0 unless.
So that means chi minus 1 belongs to k, right? That's what you say.
Yes.
From that equation, then you say chi minus 1 belongs to k.
Chi minus 1 belongs to k, yes.
Which means that chi belongs to y.
Which means chi belongs to.
Because the right side.
Well, okay. However, you argue, I was saying if there was something here, you would get a contradiction because on the one hand, chi minus 1 would be 0, but chi would be non-zero in x mod y, and therefore you would have a non-zero element of that ring. Okay. So I'm not writing. Okay. So maybe I will even write it out.
So you get chi minus 1 belongs to k.
Chi minus 1 belongs to k. Yes.
Then why does chi belong to y?
Because chi minus 1 belongs to k means this is 0. Chi minus 1 is 0 here. Which means chi
belongs to the ideal generated by these psi minus 1. Psi
yeah, but see, this is the map. See, at the level of x, if I just restrict, this is the pi restricted to x is this. So if something belongs to x and goes to 0, it must belong to y. And chi minus 1 is 0 here means chi goes to, the element chi of x goes to 0 in x mod y. See, if it were not 0, see, if chi did not belong to y, chi bar would be non-zero in x mod y. It's a non-zero element of the.
Minus 1, when we are talking about chi minus 1, that is the element of kx. But
K chi minus 1, yes, k is an element.
that is not the coming from the multiplication of x. That will be chi times 1 inverse x.
Say that again.
It's a containment, I agree, but it's not. The chi minus 1 is the element of kx, but that is not chi times 1 inverse, like, or chi inverse times 1. That you can say that. It
No,
has
that
to
I'm
be
not
zero
saying. I'm not.
in x mod
No, I'm afraid I'm not saying that. I'm not saying that. Chi, yes, of course it's not. It's chi 1 is, no, I agree. It is the difference of 2 elements there. Chi is an element of x, 1 is an element of x.
Now you said that I take chi minus 1 is in X.
No, I mean not difference in, so sorry, it's not the difference of the two group elements. I'm not saying that. See, chi minus 1 I am not claiming is an element of X. Chi minus 1 is only an element of Kx. Is that, I'm not claiming that chi minus 1 is an element of X.
Okay, chi minus 1 is an element of K.
Chi minus 1 is an element of Kx. Right? So the claim, what I'm claiming, and maybe you're not agreeing, is the following statement. If some element, let chi be an element of X. Let chi be an element of X such that chi minus 1, this is an element of Kx, not no, belongs to K. Then chi must belong to Y. This is the claim. The point of the claim being, if chi minus 1 belongs to K means chi, when I chi bar when I think of it as a restriction to Y perp, it is trivial, which means it is in the Z, it's in the kernel of this map, which means it belongs to Y. This is what I'm claiming. Okay, let's do the following. How about we take a range check on this? I've told you I hope I have said something new that we didn't have before, namely the fact that this has no p-torsion has to be used in this following way. Okay, how about we all, I should have maybe written it down rather than, okay, I saw how to sort of do it and didn't have time to consolidate it. Okay, so I will also try to write it in a way that is transparent. Okay, in the meantime, why don't you think about it, and if there is doubts, we can discuss it again. Okay, I repeat, the point I want to make is the fact that this is reduced, and therefore you have these two claims from which it follows that I of Y perp is K. Okay, any questions on what we were doing on? Okay, where were we? We had f a field E prime contained in E, finite extensions It's not clear to me where the finiteness is needed yet, but let's put that. So then we have so what I had on that side of the board, right? Universal, okay, let's see this. there is a map like that, right? Why is there a map like that? There is a natural map like that. Why? Because there is a, by the property of this, universal property of this, there is in fact a derivation, E prime derivation from here to here. By the property of this, there is an F derivation, right? So right now, say we don't have this, but if I go this way, it's an E prime derivation, therefore in particular it's an F derivation, and this you can think of as an F module. This as an E module, it's an E module. It's an E module and this is an F derivation. Therefore, by the universal property of this, there is a unique map. Okay, there is a unique map. And why is that onto? Because as we saw from the construction of the universal derivation, the module of the universal module of universal derivations or universal module of derivations, that this image, the image of this generates this as an E module. Okay, so since all those elements are mapped here, so you have generators, this maps onto generators, and therefore that map is onto. Okay, and also you have right, and then there is a tensor. So let's see what is natural here. You have, let's write this. So this is E prime. Right. So now this is an E module, therefore also an E prime module. This is an F derivation. Therefore, by the universal property of this, there is a map here. Right, and such that all the diagram commutes, right? And why is this composition 0? Well, if I go here, this is an E prime derivation. Therefore, E prime goes to 0 here. Right? So its image here maps to 0, right? And that image generates this, therefore it goes to 0. Right? So and moreover, I can tensor this with E over E prime. That is just because if I have from what we said that last time, so if you have, this is an E prime vector space. This is an E vector space, and so then I can tensor with E over E prime. I can write it on the right or left. I can be a little loose because all these are commutative rings. Exactly. If you have non-commutative rings, then it matters whether the modules are on the right or left, etc. I mean, it's important. Okay. Okay, and that is an exact sequence. Okay, the claim is that's an exact sequence. Now the reason why that is an exact sequence is that to show a sequence is exact, at least, okay, let me not say, make it more generally. Take such a sequence of E vector spaces. To show it is exact, it is enough to show that after I hom it with an E vector space, that E vector space being arbitrary, I get an exact sequence. Right? Now, when I hom it with, say, M, where M is an E vector space, this becomes derivations from derivations of e to m with derivations of e prime, and this and so it becomes the a sequence of where those harmed things are interpreted as derivations, and it's obvious that that is an exact sequence. Therefore, this is exact. The conclusion, right? This is how we got that this is exact. Yes.
You just say that this is exact directly by through these steps.
Okay, so let's see. So how do you show, for example, the kernel is precisely this? Yeah. So see, this is on to that is okay. So the exactness here is okay. The exactness here would be a problem. The fact that this goes to 0 is okay. That we just argued, I think, right? Because this goes to 0. Therefore, its image here goes to 0, but that image generates that. So all that goes to 0. So it's a complex, what is called a complex. That's clear. But what is not maybe 100% clear is that this image is precisely the kernel. Okay, maybe there are ways to show. Okay, I'm not saying no, but in any case, you harm it. When you harm it into anything, it is it's exact. Therefore, this is exact. That's the argument. I don't know if he. Maybe that's the reason why he is choosing finite dimensional, but really, I don't think the finite dimensionality is required. Anyway, in any case, we have under the let's put those assumptions, and you have what you want. Okay, definition. E field extension is separable over F if for every x in E there exists ft in ft polynomial in one variable without multiple roots such that fx equal to 0. Okay, separably algebraic is separable algebraic. I suppose he should say he's not being careful. He should say this is non-zero. Anyway, so or maybe 0 has multiple roots. I don't know. Whatever. Okay, so have you seen this definition before? Okay, you have. Okay. So as you know, if I take out this condition without multiple roots, then how does the definition change? If I cut this out, then what is it the definition of? For every x in E, there exists ft non-zero such that fx equal to 0. Just algebraic. If I cut out the separable and cut out this, I would get the definition of algebraic, right? Okay. Right.
E tensor L for any extension.
Okay. A good question. So that was why did I? Okay, that's an unofficial definition. It is equivalent, yes, it is equivalent, but it may be not easy to see. Okay, so this is the official definition in the book. Okay. Right. So here is a question. Okay, instead of saying, okay, let's make a comment and then I'll ask you a question. So remark, in characteristic 0, meaning if the base field F has characteristic 0, then every algebraic extension is separable. Okay, so what am I assuming? I'm assuming F has characteristic 0, and I'm assuming there exists, given X, there exists an F such that Fx equals 0. What do I want? I want an F without multiple roots. How do I find such an F? I can take, as you know, among all those F's which have this property, there is a unique one with what properties? Tell me what properties make it unique. Monic and least degree. That's less monic and least degree, which okay. So there exists given X in E algebraic over F, there exists unique monic polynomial of least degree monic polynomial F okay, monic means non-zero of least degree such that okay, good. Now this is just from the fact that all the F such with this property form an ideal, and an ideal in F of t is generated by monic. There is a unique polynomial of monic of least degree in any non-zero, any ideal here, in a non-zero ideal here. That is just from that. Now, why is this irreducible? Why is this Ft irreducible? You want to say that? So, as Gautam was saying, this is irreducible. Why is that? Because you have Ft by this Ft, you can map that to E by t going to x, right? I mean, and this map will be an injection, because precisely so the point is that Ft, this okay, let's call this okay, so this Ft generates kernel of phi, where phi is this map, right? So since Ft generates kernel of phi, this map is an injection, not phi, but phi is from Ft to E with t going to x. Okay. let me say that. Okay. So T goes to X. So this is an injection, and therefore the image is a domain, and therefore this is irreducible. Therefore this is okay. Fine. So that is irreducible, and now we use which shows Ft is irreducible. And if you have an irreducible polynomial over characteristic 0, then it has no repeated roots. What is the proof of that? Well, so observation, the basic observation is over any field whatsoever, f has repeated roots f has a repeated root alpha if and only if x minus alpha divides both that's a triviality, right? Because if you write f is equal to x minus alpha square into g, then you see that by the product rule that x minus alpha also has to divide f prime. Okay. So this is a general observation, and now if it is irreducible in characteristic 0, what do I know? So now continuing here, f prime, what can I say about f prime? The crucial thing is I am in characteristic 0, so the important thing I am using here is from that I conclude that f prime is non-zero, right? So f prime not equal to 0 because characteristic equals 0, right? Okay, and so f and f prime, therefore now f is irreducible, f prime is non-zero, right? That's important. If it in fact it happens in positive characteristic that you have irreducible polynomials with repeated roots precisely because f prime is 0. Okay, so this has to be equal to 1 because f is irreducible, because f prime is non-zero and f is irreducible. F is irreducible, f prime is non-zero, f is irreducible, and f prime has degree less than degree of f. That's also important. Okay. So that proves that remark, right? Because we've seen that I take the irreducible polynomial of x that has not. Okay, here is the question I want to ask you. Suppose I take a field in characteristic 0 or otherwise. In characteristic 0 there is this other argument, but suppose suppose for a minute you forgot about this, and then even in characteristic 0. So suppose I take a polynomial, irreducible polynomial, and suppose f prime is non-zero. Then you know by that argument that f has no repeated roots, right? So I attach this root alpha to it. Okay, alpha is a root of an irreducible polynomial f such that f prime is non-zero. Okay, then I know that f has no repeated roots. Question: is this going to be separable? alpha itself is okay, right? But the problem is, if I attach, if I take alpha plus 1, for example, it's irreducible polynomial. How am I sure that its irreducible polynomial has no repeated roots? Right? Correct? Okay. Right. So, but the problem is, I hope you appreciate unless you can think of some really clever way of getting around the situation. I don't know of a clever way, except of making a definition. Okay, come to think of it, the situation is analogous to the following. I say this because if you see the solution at that level, you will see the solution, what might be the solution at this level also. So, for a minute, this is something that you are familiar with, so probably you don't stop to think about it. But suppose I attach alpha. For a minute, I have attached again a root of a polynomial, right? Why is this extension algebraic? Right? Because it is finite, but that's a definition you make. Right? That's a definition you make, and then you say, oh, this is finite, therefore anything else is also finite. Right? So, you see, if you were not told about finite dimensional vector spaces, etc., if I just told you, take a field, adjoin a root, and then say, show me that everything else also satisfies a polynomial below, how would you do it? Right? So, it's something we are told, therefore, it's so ingrained in us now that we don't stop to think about it. But it's a problem so this finiteness is an extra construct which is not there in the definition. Okay? So, there is an extra construct for separability similarly, right? And that has a name, and I will mention it, and so that although it may be only implicit, I don't think he mentions the name here, it is an important definition, and it is the one that makes it plays the role of finiteness, the same role finiteness plays in the notion of algebraic extension as in the case of separable extension. Okay, and that the thing is called an étale extension. So, we can roughly say étale is to separable as finite is to algebraic. You can sort of write that. That's not a mathematical statement, it's just a So, it follows indeed that in fact this extension is separable, and the way to do it is to show that this is actually étale, and then you prove that every sub-extension of an étale extension is étale, and then you show that if it is étale, then it is finite. That's the analogous. If you think of algebraic and finite and write the proof, replace separable by étale, the same proof works. Yes. Number of homomorphisms, okay.
That if any other element beta does not have that is not separable, so it will have a multiple root. So the number of homomorphisms will reduce.
Okay, so let it reduce.
So, but for one case, I know that alpha is separable over f. So number of homomorphisms will be fixed. That is equal to degree of f.
No, this may extension may be a sub-extension, no?
Yeah.
Yeah, but every homomorphism is an extension of one of.
Yeah.
So you first attach beta and then
And then we go.
and every homomorphism from f alpha to f bar
Okay.
comes
So-
from.
Okay, you have to do, okay, you could, indeed, you could do that. I agree, you could do that with a little more. Okay, fine. So you are attaching this, right? And you are saying, okay, now go ahead. What's the argument? So the number of, suppose this was non-separable.
Yeah,
So,
this is less than the degree of f beta over f.
okay,
But we know that the number of embeddings of f alpha into f bar is exactly equal to the degree of f alpha over f because alpha is separable.
so right,
And the number of embeddings of f alpha which given a fixed embedding of f beta to f bar, the number of extensions of this is the degree of f alpha over f beta. And so the product, so it will be the product of the number of extensions. Yeah.
right,
So
okay.
if at
Yeah,
one
this
point
is indeed. So you've, right, this is how it is done in elementary books on separability, where, correct, absolutely correct. I agree with you, but that's so inelegant, right? It's a,
Why is that equal to degree of f alpha over f beta? The number of, if you fix a f beta to f alpha.
if it has a,
It will be less equal to, it doesn't matter because I have f alpha over f.
no, it will be equal to because the minimal polynomial of alpha over f beta divides the minimal polynomial.
Right,
And that
right.
has distinct roots.
right.
So
Therefore, this has distinct rules. Correct, absolutely. That, so this is separable also. Meaning alpha is separable over this field because it's separable over this. Okay? Indeed, this is the proof. I don't know of a proof. Do you know of a proof where for algebraic thing you have a proof like that? Without using finiteness, can you produce? I don't know. I'm asking. In any case, it's a proof I was never happy with because it's so ugly, it's full of. In any case, so if you use this, I mean, I'm partly saying this because just telling you that there is this notion, which if you use, I mean, you have to make a definition and prove some properties of it, but everything works out beautifully. And if you use it, things will become very clean, and you know, and that's how it's done in Bourbaki. Okay. Yeah. Okay. Okay. So now let's. So you have this map now. I'm going to write it the other way. He calls this alpha. Alpha is not an element anymore. It's this map. Right? Is this first map of a. So we have further here. Right. So I'm the map alpha. Lemma is injective. So alpha is injective. So that is notation. Sorry, that's not part of the lemma. Alpha is injective if E is separable over E prime. So is the claim clear? So this map is, so I want this, so you want the sequence will be short exact if E is separable over E prime. This thing. Right. So proof. Enough to show. So I harm it into, okay, he's harming it into E. Okay. Yeah, I see where he's using finiteness, because he's just taking the dual of this. He's just using it. So to show something is injective, these are E modules, and these are finite dimensional. He's using that. Now, therefore, I can harm it into E. Well, why are they finite dimensional? Is that clear? I suppose it is from what we have observed, right? But do you agree? Do you agree that these are finite dimensional E modules? Why is this finite dimensional as an E module, as an E vector space? It came from E tensor. Yes, yes, you're right.
So we just need Noetherian as
Um,
to say finite.
yes, you could say that is yes.
Look at the ideal I E times E.
Absolutely. So, right. So that's a good way of saying it. So what? Let me repeat the argument. So E tensor E is a finite dimensional F module, F vector space. Indeed, it's a finite dimensional F vector space. I mod I square was a subquotient of this vector space. Therefore, of this finite dimensional vector space. Therefore, finite dimensional. Indeed, that's a proof. Okay. So there may be other, you don't need to use the construction. Maybe you can use something else, namely that if you have algebra generators, or there are other ways of, even you could use perhaps even the other construction that we did as well. In any case, it is finite dimensional. This is finite dimensional over E prime, and when I tensor this with E, it is going to be finite dimensional over E. Right. So these are finite dimensional modules. So enough to show that this is surjective. Right. So what does that mean? That is, so ETS means enough to show, that is every F derivation E prime to E can be extended to F derivation of E to E. Okay. So the idea here is that you can extend derivations, right? So okay. So what is the idea here? So let's again, I may not do the full proof. I'll just do the basic idea of the, there is one basic idea, and if you observe that, the rest of the proof is just formal. Okay. So what do I know about E prime over E. This is separable, right? For a minute, let's assume that you have right. So, this I can think of as, I mean, I can do it with alpha first, then with, so to extend it to E all the way, this is a finite dimensional extension of this. First I can attach an alpha, extend it to that, then I can attach a further attach it to that. So, it's enough to assume, enough to do it in this case. Okay. So, this is what? This is E, I can write this as E prime t by Ft, where I can assume that Ft has distinct roots. If necessary, I can even assume it to be irreducible, but right. Okay. So I want to, what do I want to, so observe that E prime, sorry, this thing, this is E now. E is generated by E prime and alpha, right? Everything is a polynomial with coefficients in E prime in alpha, polynomial in alpha with coefficients in E prime. Now, I want to extend a derivation. So, think of a polynomial in alpha that looks like this, right? Where these coefficients are in E prime. If I am going to apply some derivation to it, right? So, how does it going to look? It's going to look like dA naught plus dA1 applied to alpha plus A1 d alpha, right, and so on. In other words, if I know how it's going to act on alpha, I am done, right? The problem is to define. So, if I know how it acts on alpha, that determines the derivation. The problem is it must be consistent, right? I can't arbitrarily define it on alpha. There are constraints, and I have to make sure those constraints are matched, I mean are satisfied. That's the problem. So, let's see if those, what constraints should they. So, if I am going to take d of f alpha, right, what is this? So, let us see, if I want to write this as x minus, so f of t, right. Just one second, let me write this like this and then see if I. So, okay, you just follow your nose. I'm just trying to. So, I want this to be 0. Okay. Yeah, I can't think on my feet. Okay, so he writes the following. So right, so let's look at let's look at this. Okay, so I take GT here. Define and only if, okay, define dg, he says define dai, so gt is equal to, I'm a little confused with this, I bigger than or equal to 0 ai ti, so define dai ti, okay. Then d is extendable to an f derivation of e prime in e with d prime x equals a if and only if okay, so right. So let's just follow what he's saying. So I'm given d in derivations of here e prime to e. Given this, define dg to be this. Okay. Now then claim is then d is extendable to an f derivation to an f derivation d prime of e in e with d prime x is equal to a if and only if, okay, let's see, f prime x a plus df of x equal to 0. Okay, let's understand this statement. Okay, so given this, you make this definition. Okay. So that's like saying, okay, let's see, he's okay. This is not the way I would have done it, but anyway, so he's making this definition, and so where you write G like this. So we have to understand this claim. So let's see if that is clear. So okay, so what is d prime of f t? It is with d prime of x is a x is, I guess, alpha, right? With d prime of x is equal to a. So the d prime of alpha, this is our alpha, right? Right. So if I think of this, okay. So this is this. I evaluate at alpha, and this. Okay. So I see this now. So what he is saying is the following. Okay. Let's look at G, right? G, I write G like this, and I write dG to be this. That's just notation for the moment. Okay, so if I have a d prime, so let d prime be the extension of E in E, right? Okay, the E prime extends D. How will it act on G of alpha? G of alpha is an element of E, right? How will it act? Well, G of alpha is AI alpha I. Okay. Now, if I apply D, okay, so there is one on the one hand. So there are, you sort of split it into two pieces. Each one gives you two pieces, and you collect DAI, TII, you collect and you get DG of this. And on the other hand, if I do that is the derivative times d prime of t. I mean, there I have alpha. So is this. So that d prime of GA is therefore equals G prime of alpha d of A plus dG of alpha. D prime D, one second, G prime of alpha one second, G prime of alpha D of alpha, I mean D prime alpha, okay. Now right, if there is a D prime, it looks like this, okay. Now I want this to be 0, right, why? Because for the, when I put it to F, right, so I know that F of alpha is 0, right, no F of alpha equal to 0. So I want this to be 0. So that is F prime alpha D prime alpha plus dF of alpha equal to 0. okay, and then okay, the point is I have to find A, I have to solve for A, right? So I can write, if I want to solve this for equation for A, then I have to divide by f prime alpha, and the point is f prime alpha is non-zero. Okay, so so d prime alpha therefore has to be, so I mean so far we are only deriving a necessary condition. We'll then it should be easy to just check that it is sufficient. So this is df of alpha by f prime alpha. Okay, so I make this is but then he is saying if and only if. So the claim is that it is also sufficient. Okay, so why is that? Suppose I make this definition, then I know this holds. Once this holds, then I know that the derivation I have from, so from E prime t I can define a derivation. I can basically send d prime of t to anything, right? I can extend see if I am I can get a derivation from Et to E, right, that is determined by where t goes, but there are no constraints whatsoever on where t can go, right, because it is a free, you can basically send t anywhere. And so the only question then is that if I send it to A, will that pass down to, will that derivation pass to E? So in other words, it has to be 0 on the ideal ft, and this is equal to this. And so if I have, okay, let's see. So let's just check that it passes to the quotient. So that means it has to, if I have f times, let's use a ht, right? I take a d prime there. I want to check that this is 0, right? It's enough to check. Is it obvious? How do, because f of alpha is 0. Very good. So if I once I know that d prime on this is 0, the other one is d prime. Once I put in alpha there, it is 0, right? So this is, it's obvious, and therefore there is okay. Yeah. Okay. Okay, perhaps it's good to think through this proof in yeah, it's a little complicated. I mean, it looks a little assume that D is actually an E prime derivation. Assume the simpler case is when D is an E prime derivation, then you would be forced to say that this is actually 0. This is actually 0, so you would be forced to send alpha to 0, D of D prime alpha to 0. Okay? So, in other words, an ascent a priori, I mean, on the face of it slightly simpler, but maybe essentially equivalent to this statement would be, if I have a finite extension, then there are no finite separable extension f to E, then what are the f prime derivations from E to E? So I didn't say that correctly. So, if I have finite separable, right. So, what is this is 0. Right, because where would you send the generator alpha? You would have to send it to, so claim is this is 0. This is what the proof shows. Okay, and so maybe we should just intuitively first, if I had better prepared, I would have just seen this and then done the proof. Okay, that would have been better. I would have also have not gotten stuck as I did. Okay, so what is the proof of this? Well, you can think of E as f of alpha. In fact, you can do that. You can do, but for a moment, let's just not worry about how you can do that. Just assume this. Then, where would you? So you have this map, right? It is determined by this. Okay, I want to show this is 0. To show that this is 0, it's enough to, because I know that this, it is generated as an E module by images here. It's enough to show that all the images are 0. Okay, and this map is D. I'm omitting the E bar. Now I know that D of f is 0 because they are all f derivations. Okay, so if I show that alpha is 0, then since this is generated as an algebra by f and alpha, everything will be 0. Okay, and why is D alpha 0? Well, you know that f alpha is 0, and where does D go? So D of f alpha therefore is D of 0, which is 0 on the one hand, but this by calculus, if you wish, it's f prime alpha D alpha. But this is a non-zero element of the field E. This is an E module. Some non-zero element of the field E times D alpha equals 0, therefore D alpha is 0. This is the basic idea of what is involved. Okay, the rest is just jazzing it up. Okay, let lemma, let E be equal to f of x, then, so this is, I am not writing square bracket but round bracket. Okay, what this means is that x is an element of E and E is generated as a field by f and x. Then dimension of is less than or equal to 1. we have equal to 0 if and only if E is separably algebraic over F. Okay, proof. If X is transcendental over F, right, then okay, let's do it in this case. What is that? F is transcendental over F. Then what is this? This is just the, yes, this is the polynomial ring over F. This is the polynomial ring of F. So this is equal to free module with one generator over Fx. So you can write this Fx dx. So free module okay. Now the point is, if I take a what is I claim that. Right. So what? So I claim. So let's claim this. I put the field here. So what I'm claiming is that over the field, it is just a one-dimensional vector space over that field. Okay. Why is that? What is involved in? Again, to see this is the same thing as seeing the following. Both sides are modules, both sides are vector spaces over Fx, right? So to see this is the same thing as seeing, if I hom it into if I hom both sides into a vector space over Fx, what do I see? Homing, so to prove the claim, okay, at least is one is there is a map in one direction, right? There is a map from here to here.
Same calculation that we did for linear methods to show the exactness. So first we formed it with any arbitrary E model, E vector space, and there don't we make the same checking?
No, there is just a little bit extra. Well, what we saw was this side is equal to Hom. I mean, what we see, I mean, there is a bit extra that we have not seen yet. It's the Homing part maybe we have seen. The part that I'm going to make the change also we have seen, but there is something extra that we have not seen. Again, it's quite easy and trivial, but that's something that we have not seen. So, pardon me?
Omega fx over f, again if round bracket is dx. Because x can again go to.
Yes, that's correct. That's correct. That's the. Have we seen it before? That no. So the point is that if you know how it acts on polynomials, you know how it acts on rational functions, because you are bound by the quotient rule. That's the new point. That maybe I mentioned it. I don't remember, but that part is not there in that exact sequence. Okay, but indeed, that's so. This is, that the formal statement of what you're saying is this, right? This is exactly formally stating that, right? Okay. So more precisely, there is a map in this direction, right? There is a natural map in this direction. When I write equality, what do I mean? I mean that there is a map which is an isomorphism, right? What is this map? There is a map because that part is like there is there will be right. I mean, there will be, so to see the map, there is this derivation here, right, and there is this derivation here, this derivation, both are d's, this is contained in here, therefore, and this composition is a derivation, therefore there is a map here, right, formally. This is just like in the previous case, right, in the exact sequence, whatever it will be. Moreover, this is an fx module, this thing. Therefore, I can transfer this with f of x, and there will be a natural map, right? So that is this natural map here. And when I write equality, what I mean is that natural map is an isomorphism. Okay. So to prove the claim, that is that claim, enough to show after Homing with with a arbitrary fx module, fx vector space M, right? But what is this? So if I do that, then Hom fxm is what? That is derivations from fx to m. So what I have is f derivations from fx to m. Okay. Now Hom of fx to m of this is the same as, you can remove this and then write Hom as f square bracket x of this to m, right, which then is just derivations of, so there is the natural map here, derivations of f of fx to m. Right? The claim is this is an isomorphism. And that's a check. So what I'm saying is this is equivalent to this being an isomorphism via this observation, but that is easy to check because this map is an injection. Let's see. What do I have to? Well, it's actually this map. The natural map is this way because I've harmed it. Harmed it, that's the natural map. So that map is the restriction map, right? Is the restriction map. And what do I have to show? It's injective and it is surjective. So it's injective means once I know it on fx, it is determined on f round bracket x, which it is because once I know it on fx, then the quotient rule takes over and I know it on f round bracket x, right? And it is also surjective because I can extend it using the quotient rule once again to fx. Okay, so this is a check and use the quotient rule. So that proves this. Okay. Oh my God. Okay, I'll stop in. So that does that. Okay, let's see, where were we? If x is transcendent over f, then we have, in fact, what have we shown? That this is equal to 1. That's what we have shown, right? Okay. In any case, okay. Okay, let's see.
We want to show dimension as well.
Yes.
Then that proves entire level.
Yes, that
Because if it is separable algebraic, we know it is 0.
it's separable algebraic, we know it is 0, yes.
If it's transcendental, we know dimension 1.
Yeah.
If it is, then we just have to show that algebraic non-separable also dimension is 1.
Right,
Then
right.
dimension will be less than or equal to 1 and 0 if and only if.
Right, but rather than think like that, let us show, I would rather show that it is first of all less than or equal to 1 in any case, right? And the proof of that involves this. Okay, so let's see if I okay, what I am going to claim is that it's okay. So I am going to claim that this map here is injective in any case, right? What is involved in that? Okay, once I know it on x, I know it on, see, it's the quotient rule again, right? So this map is going to be, so he also doesn't write out too much. He says, we are in two separate cases. But the point I want to say is that this map is injective in any case. See so what did we use here when we said, so we said that, see, the point being, so no matter what x is, x could be transcendent, Right. Correct, but I'm not using, without reference to it being algebraic or not algebraic or anything. right? I mean, just as an abstract without reference to anything else, ab initio, it is injected. This is what I want to say, because of the quotient rule, okay, which means that this is surjective, right? This is surjective, and this is dimension 1, therefore this is less than or equal to 1. Okay, that's okay, but still it remains to see that so now going back to okay, now what is the proof that it is 1 if it is algebraic but not separable, right? Okay, the proof goes as follows. We derived that necessary condition, right? What was that? That was like saying f prime alpha times a equals 0, right? But if f prime alpha is 0, that's no condition at all. So you can choose, see, so the f prime alpha times a, where a was the image of a was f prime alpha d prime alpha was equal to 0. That was it was a necessary condition on d prime alpha. We wrote down an equation, right? We are in the situation where we are we are in this simplified, where this d was actually we are, see, in the proof that we did, d was an f derivation and we are over e prime to e we were considering, but then we saw how to simplify it when f and e prime were the same, and in this situation we are in the situation where f and e prime are the same, right? So this equation will become f prime of, if I am attaching alpha, f prime of alpha d prime of alpha equal to 0. That is the condition for d prime of alpha to be satisfied if there is an extension of the derivation d to d prime, where for the d prime alpha has to satisfy, if and only if this d prime alpha satisfies this condition, and indeed that's no condition at all if f prime alpha is 0, right? So it will be 1.
Now we are in the case of algebraic and non-separable.
Algebraic non-separable.
And so what is 1?
The dimension. So there will be an, okay, maybe because see, if it's algebraic non-separable, this one there will be an, you can write f of x, right? And when can it extend? Maybe we'll do this first thing next time. We'll come back to this because we're already over time, but the idea is that you can, the if and only if condition that we wrote down, yes, but f prime alpha is 0. See, the sufficient, the necessary and condition, okay, what this condition was, d extends to d prime with the, if and only if, right, f prime alpha d prime alpha equal to 0. If I can find a d prime alpha which satisfies this, then there is an extension, right? But f prime alpha being 0, this is no condition at all, therefore there is an extension. You are basically free to do what you want to do. Okay, that's the idea. Anyway, we'll write this out more carefully next time. That we'll start with that. Okay, see you on Wednesday. Okay. In the meantime, I'll think about the solution that I gave. I will write it up, and also I know I have one more question to think about.